All right, this is the second lecture on hypothesis testing. We're going to continue talking about some terminology and just the general concepts behind hypothesis testing, but I'd like to start by just working through another example very similar to the example that we worked through last time. So we're just going to use the same steps and go through another empirical example. So remember, this is the testing procedure. This is the same slide I showed in the previous video. We're just going to work through this. I'm not going to read it this time since it's the exact same thing, but just a recollection that we've got this sort of detailed recipe to follow. So let's just go through an example where we ask a question: do dogs resemble their owners? And this is some pet food advertisement here to make the point, but occasionally people make the claim that people choose pets that resemble them. So someone actually went and studied this. The experiment was to look at 41 dog owners in parks, and they took a photo of the dog and the owner separately and on a blank background, so there's no sort of cues from the background. And then for each trial, a student was shown three photos. One had the owner, one had their own dog, and the other photo was a photo of another dog. And then the student tries to match which dog they think belongs to the owner based only on appearances. So remember, the first step in our hypothesis testing, we're going to state our questions in terms of the null hypothesis, H naught, and the alternative hypothesis, and choose our significance level, alpha, for the test. So we're going to remember the null is going to be a statement about the population proportion, and it's going to be a very specific statement. So an appropriate null for this would be dogs and their owners show no sign of similarity. The proportion of correct matches is 0.5, and remember this P is the population proportion, not the sample proportion. The alternative is that dogs and their owners show some sign of similarity or dissimilarity, so it's just everything else. The P does not equal 0.5, okay? And then we use I should have explicitly put it on the slide, but we use alpha of 0.05 for this test, which is kind of the convention, but it's not required to use that alpha. All right. So step 2 is to collect a random sample. We mentioned the researchers already did this. They collected a sample size of 41 students that were shown pairs of photos of dogs and tried to match with the owners. Okay, and I didn't tell you this before, but there were 23 correct matches. At least I don't think I mentioned that datum. All right, so the descriptive statistics and the test statistic in this example, it's really simple. It's just the number of matches, or we could use the sample proportion, 23, that's X over N. Number of successes over the total number of trials, and that's 0.56. Okay, so it's not exactly 0.5, but this is the sample proportion. So just because it differs from 0.5 doesn't mean we're automatically going to reject the null hypothesis, because the null hypothesis is stated in terms of the population proportion, right? All right, so the crucial step in hypothesis testing is determining the p-value. What values of the test statistic are expected under the null? How does the test statistic differ from the null distribution? And what's the probability of observing a value of the test statistic as extreme or more extreme if the null is true? That's the definition of the p-value, and that's going to be the crucial thing that's going to allow us to decide whether or not we accept or reject. Okay, so this is the null distribution for our 41 trials where there's a 50% chance of a success on each trial. And so because it's an odd number, n equals 41, you don't see 41 labeled here on the axis, but half of that is right here at 20.5. So actually 20 and 21 both have the equal probability. They're both the mode of this distribution. Okay, so that's the null distribution. We're going to cover in the next chapter how we calculate the heights of these bars, but right now we'll just assume that this is given to you. Okay, and so the data was 23. So if we want to think about what the probability of seeing something that's odd as 23 is, well, there's 23, and more extreme would be 24 or 25, all the way out. So this whole entire upper tail of the distribution gets colored in red because that's going to contribute to our p-value. But remember, we're interested in deviations in any direction. 23 is higher than we expect, the expectation being right here in the middle, but a lower value that's equally distant would also be surprising. So that's a value of 18. So 18 and 17 and 16, etc. So this tail also contributes to the p-value. So graphically, the p-value that is shown in red here, if we were to sum up the heights of those bars, okay? the way we actually calculate the p-value, we don't just color them in on the bars. We have to think about, okay, what is it? Remember, it's the probability of any outcome that's as or more extreme than the actual outcome. This 23 is our observed data. So that would be the probability of getting a 23 or 24, et cetera, all the way up to all 41 of the trials were matches. And the other side of the distribution, the other tail of the distribution is 18, 17, all the way down to 1 or 0 matches. Remember, where does this 18 come from? This is exactly the same logic we used in the wrestling example in the previous video. The expected value of the matches under the null hypothesis, the expectation for null, is the trial size times the probability of a success given the null. So that's n equals 41, and there is a half success if the null were true. So that gives us an expectation under the null of 20.5. Our observed value is 2.5 above 20.5, so going 2.5 below that same number is equally extreme as what we actually observe. So 20.5 minus 2.5 is 18. That's where this 18 comes from that tells us the other tail of the distribution to sum up. So just going back to the graphical version, this was our data, and everything that's shown as red is not necessarily what we observed, but it's as extreme or more extreme than what we did observe. Okay, so you get some pretty big probabilities here for the ones that are close to the expectation. The chance of getting 41 matches just by random is minuscule, or equally minuscule is the probability that you get 0 matches if you just had a half chance of guessing correctly. But you sum all of that up to get the p-value, and it's 0.5327, so over half the time. Okay, so now step 4 is make the decision about the null hypothesis. Remember, the p-value measures a discrepancy from the expectations of the null in terms of how rare this event would be, seeing something this weird if the null were true. If the p-value is really small, smaller than our threshold alpha that we chose, then we reject the null. If not, we do not reject the null. So 0.53 is much larger than 0.05, so we do not reject the null hypothesis. So that's our decision step. And then, it's really important to be able to tie this all together and summarize it and make sure it's not just a bunch of mathematical steps. We got to answer our question, report the results in the conclusion, and this is once again a repeated slide from the previous video. We want the conclusion to have our sample size, relevant descriptive statistics, the test statistic, the p-value, and a clear statement of our decision. If we reject the null, then we state what direction the data deviated from the expectations of the null, so larger or smaller or whatever. So for instance, this might be an appropriate conclusion for this study. For 41 sets of photos that included a photo of the dog owner, that owner's dog, and an unrelated dog, participants were asked to identify the dog which belonged to the human. 23 of the participants correctly matched the owner with their dog. The proportion of matches, 56%, was higher than the expected value, 50% under the null hypothesis, that there were no visual clues that the dogs match. However, the difference was not statistically significant. There's our p-value. P is 0.53. So we cannot reject the null hypothesis that the appearance of dogs and their owners is no greater than one would expect by chance. Okay, so we've got our sample size in here. We've got our summary statistics and descriptive statistics and the test statistic, which is 23. We state what the null is and the p-value. And since we don't reject, we don't need to emphasize the fact that it was higher than 50%. It's fine to say that, but we're not putting any biological significance in that because it's not a statistically significant result. It's really plausible that you would see this kind of deviation just by chance. If the null were true, about half the time we'd see this much deviation, right? The p-value is 0.53. So this is not at all unusual data if the null were true, so we shouldn't really doubt the null based on these data alone. Okay, so remember, if we don't, we don't say that we accept the null. What we say is we fail to reject it. We don't know if the null is true. And we don't say that we reject the alternative because we certainly don't know that the alternative is not true. Perhaps there is a very slight preference for, the alternative might be true. The resemblance might be really slight, or it might only happen in some rare cases. So maybe the true value is 0.52 or 0.53. We definitely can't reject those values. The empirical fraction in the data was 0.56, so certainly we wouldn't want to reject that. Remember the way the whole procedure is set up, we're just testing the null. And if the null looks really incompatible with the data, we say that we reject the null. And that didn't happen in this case. So we're left in this sort of unsatisfying result of just like the data don't disagree with the null might be true, the alternative might be true. We have tested the null and the null has failed to be rejected, but it doesn't necessarily mean it's correct. All right, so there's a little more jargon in this chapter that we're going to use a lot through the rest of the course, so it's important now that we've seen a couple of examples to talk about a little more of the terminology that we use and just sort of concentrating here once again on the higher level perspective of what this whole testing procedure does. Okay, so the possibilities when we do a test, we never know which of these possibilities actually happens. It's either the null can be true or the null can be false, right? Those are our two options. We don't know which column we're in. And if we compare the truth versus our decisions, well, our decision is either to reject the null or do not reject the null. So if the null is true and we reject it, we've made an error. Or if the null is false and we do not reject it, we've made an error in some sense. We failed to reject it. So in other cases, we're getting it right. So there's little green check marks here that say, okay, the null was true and we failed to reject it. That's what we want to do. The null was false and we did reject it. That's what we'd like to do. But there's sort of two types of errors that we can make in this inference procedure. And statisticians, being terrible at naming things, gave them very boring names. So the first one's called type 1 error. That's when we reject a null hypothesis that is true. And the second one is called type 2 error. That's when we fail to reject a null hypothesis that's false. So type 1 error, falsely rejecting a true null hypothesis. The significance level of our test, which we've been denoting alpha, that controls the maximum type 1 error rate. And often we set that to 0.05, as we've said numerous times. So we can choose what the alpha is. We choose that before we do the test. And remember, that's the threshold for when the data look really weird under the null hypothesis, we reject the null hypothesis. But the probability of getting something out there, we never set alpha to 0, because then we would never be able to reject anything. Our p-value is never going to be 0, so we would never reject the null hypothesis. So it's always some positive number, and so that all means that even if the null is true, there is some small probability, that probability of exactly alpha, that we reject the null, even though it's true. So alpha is controlling our type 1 error rate. And so the type 1 error rate is when we reject a null that's true, and the probability that that happens if the null is true is alpha. Sometimes you'll hear people say that alpha is the probability of a type 1 error. Well, it's not really the probability of a type 1 error. Alpha is the probability of a type 1 error given that the null hypothesis is true. So it's in this condition. There's alpha probability that we reject the null and a 1 minus alpha that we fail to reject the null. So if we want to avoid this error, we set alpha to a really low number, so then there's a low probability that we'll have a type 1 error. Okay. But the downside of that is we're increasing the threshold. The p-value's got to be smaller and smaller. If we set alpha to 0.01, then we've got to have really small p-values to ever reject the null. So that makes it harder to reject the null. So there's a downside to setting alpha really low. Okay, type 2 error, as I mentioned before, failing to reject a false null hypothesis. And we call the probability of a type 2 error when the null is false, given that the null is false, we call that beta. We don't talk about beta nearly as much as we talk about alpha in this course because we don't usually set beta. We usually choose the significance level for our test. We control the type 1 error rate, but we don't directly control beta. It sort of emerges from our sample size. In general, smaller beta means more statistical power. It's a less chance that we're going to make this error, fail to reject a false null. So power, in the statistical sense, is the ability to reject false null hypotheses, and power is 1 minus beta. So when people talk about the power of a test, it's essentially what's this probability of rejecting the null when it's false. So it's 1 minus beta, where beta is the probability of a type 2 error when that null is false. Okay, so just to go back to this table and tie together all these terms, we talked about the fact that if the null hypothesis is true and we reject it, we've made a type 1 error. We can control the maximum type 1 error rate by controlling alpha. We get to set that. And then what emerges from the power of our design is some probability that we're going to fail to reject null hypotheses that are false. Of course, sort of depends on how wrong the null is, how easy it is to detect it. So it's hard to calculate the power directly because you sort of need to know which alternative is actually correct. In the matching example, if the true matching probability for the photos of the dogs and their owners was 0.5001, well, technically speaking, the null is wrong, but it's just very close to 0.5, so we'd need enormous sample sizes to detect that. So we'd have low power to detect a really slight deviation from the null. If you're considering an extreme deviation from the null, what's the probability of matching correctly of 80% or something like that, then you have a lot more power to detect that. So the calculating the beta is really tricky and involves thinking about what the alternatives you're interested in are, and so we really focus a lot more on controlling the type 1 error rate. Okay. Another bit of jargon that you hear a lot in reference to tests is this concept of one-tailed versus two-tailed test. We almost always have a situation where we set up the null as some parameter equals an exact value. We're interested in a very specific null, and the alternative is just anything other than that. So deviations in both directions away from x cause us to doubt the null. So, too high or too low, data that looks like looks like the true value is larger than x or less than x would cause us to doubt the null. And so there's two tails to this test, where either direction were causing us to doubt the null. That's a two-tailed test. And so remember when we were talking about correctly matching the photos, there was our observed data. We counted this tail as more extreme, but we also said, we would have doubted things if they were on the other side as well. And so that is also as extreme. And so there's two tails that contribute to the p-value, and there's two directions of the data deviating from the expectations of the null that cause us to doubt that the null is true. In very rare cases, deviations in only one direction are just so implausible that you'd only explain them by sampling error. So you're basically saying that you're only concerned with deviations in the other direction. So the null hypothesis is something like some parameter has a value of x, and the alternative is just that parameter is greater than x. So only deviations in one direction matter to you. So if that were the case, if you were doing a one-tailed test here, it would just be deviations in this larger direction. So if you think about what's going on here, the p-value for this test is 1/2 what it was before, because we're only summing up those probabilities. We're not summing up these probabilities in a one-tailed test. So typically, the p-value for a one-tailed test is half the p-value for a two-tailed test. So since we get lower p-values allow us to reject more, it says, oh, well, that'd be great to have lower p-values, so maybe we should just do one-tailed test all the time. That's not the way to think about it. We're only allowed to do one-tailed test if we're ruling out the possibilities in one direction beforehand, not looking at the data. We're not allowed to collect the data, see how it deviates from the null, and then decide to do a one-tailed test in that direction to increase our power. It's really rare for there to be cases where a test are legitimately applied in the one-tailed direction. So one example, your book gives one about machines, or you can imagine like if someone's playing an online game that involves someone flipping a coin and they have video cameras watching or something like that, call the coin in the air. Well, we wouldn't want people with good cameras and good computational machinery to be looking at the coin in the air and trying to use physics to estimate whether it's going to land heads up or tails up. We want the coin flip to be 50-50. So you might be interested in studying, how well they call the coin in the air, and if it's greater than 0.5 that they get it right, in a statistically significant sense, then maybe they're cheating in some way. Maybe they're using computer equipment or something to call it in the air, and they're getting an unfair advantage. Presumably, they wouldn't be using that method if it worked less than 50% of the time. So you're not really suspicious when they're calling it in the air and getting it wrong most of the time. So you're only interested in one tail. It's just really rare in this course for us to use one-tailed tests, but you'll see them referenced in the literature, so we feel like it's important to discuss it. Okay, and another little wrinkle that to not get confused about, you'll see this in a few chapters, in just 2 chapters from now. Often two-tailed tests, it means that both tails of the test statistic contribute to the p-value. But for some of the tests that we use, for instance, chi-square tests, we can think about the nulls as that there's specific expectations, and the alternative is anything else. But any deviations from the null cause an increase in the test statistic value. So we'll see that was not the case for this coin flipping example. But there's a case where the hypotheses are set up to be like any direction that counts, it makes us doubt the null. So it's all directions hypothesis test. Any kind of deviation causes us to be suspicious. So that's how we usually want to run our test. But it turns out when we calculate the p-values, we're only going to be looking at the right tail because any discrepancy increases the test statistic. So this will make a little more sense in chapter 8 when we talk about the chi-square distribution, but this is a chi-square distribution with what's called 5 degrees of freedom. We'll discuss that later, but we only count the right side of the tail. And that's not doing an inappropriate sort of one-sided test. It's because the way this test statistic is built up, only one tail of the null distribution counts. So there's this subtle distinction between what's really suspicious is when you set up things and you only consider deviations in one direction. That's almost never justified, and so that's what you really need to be watching out for. Not so much test statistics where all of the probability for the p-value is on one side. So, okay. And a little more terminology before we finish up this chapter. We're going to see a lot of the usage of the term critical value in this course. For a particular test, a critical value is the least extreme value of the test statistic that gives you a p less than or equal to alpha, right? So remember, we're setting alpha, our significance level for the test, and that becomes the threshold for the p-value. Whenever the p-value is less than alpha, we reject the null, and we get to choose our own alpha, right? And so that's the fundamental decision we make. But the critical value is another threshold. It's a threshold not for the p-value, but a threshold in terms of the test statistic. So I think of it like exchanging currency or something. You're moving to a different measurement system. The fundamental one is comparing alpha to the p-value. But if we're trying to think about what our test statistic is going to have to be in order for us to reject the null hypothesis, we can translate that into the realm of test statistics, and the critical value is the threshold, the least extreme value that causes you to reject. So we can calculate the critical value from our study design and alpha. It's not something about our specific data. It's about our sample size and the alpha that we've chosen and how we're doing the test. So for instance, if we thought about the correctly matched dog photo example I did before, and we said, okay, we know our sample size is going to be 41, we can figure out what the null distribution looks like before we see the data. And we can think about, well, if we got an x value of less than or equal to 13 or an x of 28 or higher, then this would be the p-value we'd get. We'd shade in this 13 and over and 28 and higher. Those are the two tails of the distribution that would contribute. And so that would give us a p-value of 0.0275. So since that's less than 0.05, we would reject that hypothesis. But if we get data that's a little bit closer to even, 14 or 27, now the tails have gotten a little bigger, and we can see that the p-value would be 0.0596. So that's greater than 0.05, so we would fail to reject, right? So if we get data as like this, we would not reject. If we get data like 13 or 28 or something more extreme than that, we would reject. So what that means is that the critical value for this study design with a null hypothesized value of 0.56s on each trial and 41 samples, then the critical value is either 13, or you could say the critical value is 28. Since it's a two-tailed test, those are both equivalent statements. And note, often we said that X, the data that we observed, is 23. So usually the test statistic coming from our data looks like that. It has no decorations. When we have the test statistic name, but with a subscript that looks like a alpha value and a number of tails, that's a hint that we're talking about a critical value. Here we're saying, not specifically in our data, we're just saying that if we get data more extreme than 13, or if we get data more extreme than 28, then we're going to be able to reject. Okay, so the critical value, in some sense, is a threshold, just like the alpha versus p, but it's kind of one that we can calculate just to make things a little more tangible for us to move out of the realms of probabilities. And it turns out that the way we're going to conduct a lot of tests is looking up critical values in tables in the book. So it's important to understand this concept. So remember, this is something that you can calculate from the null hypothesis and the sample size. It's not a value that refers to the test statistic you calculate from your data. It's a threshold for what your test statistic must exceed in order to get significance. Okay, so those are the main concepts of Chapter 6 on hypothesis testing. In the next chapter, we're going to see how to calculate these null distributions for a particular type of test, and that's going to be the sort of the first chapter in this book where we start working through particular problems. How do we actually do a hypothesis test with no one telling us the numbers behind it? So it's going to be applying all these concepts from Chapter 6, but to a specific case. So make sure you're feeling confident on these all this jargon and all the concepts behind this chapter, and come see us in office hours or ask us questions in class if you have any questions. All right.